Chapter 13, Universal Gravitation. Newton's law of universal gravitation states that every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. For example, if we have two particles of mass m1 and m2, and with a separation of r, mass m1 will attract mass m2 by a force, we name it F12. That is a force 1 to the 2. According to Newton's third law, when one particle exerts a force on the other, as a reaction, the other particle will exert a same magnitude but opposite direction force. We name it F21. Now, in this case, F12, the magnitude equals to of F21 because that is a pair of action-reaction forces. However, the nature of this pair of attractive forces is gravitational force. According to Newton's law of universal gravitation, it follows this formula that is proportional to the product of their masses and inversely proportional to the distance squared. And when we say proportional, then we can place a constant. In this case, we use a capital G. It has a special meaning. I will explain that later. Then we will make that equation. Now, first of all, let's discuss about mass. Well, in SI unit, mass is in kilogram. In this case, as a matter of fact, the mass is gravitational attraction mass. It is different compared to the inertia mass that we learned from Newton's second law. However, when we use SI unit in kilogram, somehow the particle's gravitational mass equals to its inertia. So we can safely use its inertia mass for the calculation. Secondly, the inverse square law, it is a very interesting situation. It will give us a consequence that the gravitational force exerted on a finite-sized spherical symmetric mass distribution. For example, let's talk about Earth. Earth is very close to a spherical distribution of mass. Now, the gravitational force exerted by a finite-sized spherical symmetric mass distribution on a particle outside the distribution is the same as if the entire mass of the distribution were concentrated at the center. So, in the future, when we have a spherical distribution, we can safely, if mass is uniformly distributed, we can safely assume that the mass of this spherical distribution as if concentrated at the center. So, mass of the Earth we can mark at the center. Therefore, if the particle of mass little m has a distance of h, which in this case we call this altitude, above the surface of the Earth, and the distance from the center of the Earth to that particle, obviously that little r equals to radius of the Earth, which is this part, plus altitude h. That is the separation between mass of the Earth and that particle of mass little m. We're going to have a chance to prove this theory. This is called Newton's shell theory when you learn physics 1c. Now, another interesting constant here is a so-called universal gravitation constant, capital G. Measuring this G requires relatively accurate and sophisticated equipment. Well, that was actually done in the year of 1700 in the lab of called Cavendish Laboratory. And the result is quite astonishing. That capital G in SI unit equals to 6.67 times 10 to the negative 11 of so-called SI unit. This capital G must carry units to balance the left and the right side of the equation. Let's take a look. If the left side of the equation is in Newton, well, Newton actually is kilogram times meter per second square. Well, on the right side, we have mass times mass, which is kilogram square, and this is in meter square. So the G has to choose the SI units that balance the left and the right. Now, how do we calculate the gravitational force between a point mass and an extended body? For example, this is a one-dimensional ruler of mass, let's give it capital M, of length capital L. Let's establish a x coordinate, which is one-dimensional. This is x equals 0, and obviously this will be x equals to L. Assume that we have a point mass located a distance little b away from the far end of this ruler. Now, what is the gravitational attraction between the ruler and this point mass M? Well, some of you might think, well, since this is a uniform distributed ruler, the center of mass should be here. Can we just assume the total mass, capital M, located right here, and then we directly apply the Newton's law of universal gravitation that we just learned, which is Fg equals to the capital G times M1, M2 divided by their separation square. In this case, it looks like it's half of the length of the ruler plus b. Well, I'm going to prove it. That cannot be done because we just learned only when we have a spherical symmetric mass distribution that we can assume that its entire mass of distribution were concentrated at the center. This is a one-dimensional ruler. It's not a spherical symmetric mass distribution. Therefore, we cannot assume the gravitational mass concentrated at its center and directly apply the Newton's law of universal gravitation. What we need to do is we have to cut a very small piece, name it dm. Since it's so small, that is as a point mass. So let's calculate what is the gravitational attraction between this point mass dm and that m. Well, since both are points, so we can directly apply this equation, which is Fg, gravitational force, between these two point masses. Let's say that is the dm attracts on this little m, okay, that is called df. So let's name this dfg equals to a capital G and two point masses. One is the point mass m itself, the other is the slice we cut. We name it dm, very small, so this as if m1, m2, divided by their separation square. And right now, the separation should be between dm and this little m. So it should be L plus b minus x. Inverse law square, don't forget our scale. Why is that? Because that the length of ruler is L plus b and give you this much. Where do we cut this dm? We cut this dm x meters away from the origin of the x-axis. Therefore, L plus b minus x give us the separation between dm and this mass m. Okay, so we established the force between this dm and this m. How many pieces of dm that we have? As you can see, many pieces. So we have to add all of them. Now be very careful, this dfg is a vector. However, you can imagine if we cut another piece and look at the blue one. If this is called dm of prime, well, if that point mass exert a force on this m, let's call dfg of prime. Well, because this is always attractive force, so the dFg prime has the same direction as dFg. So these two forces can be added directly because they have the same direction. Therefore, we can safely add all the dFg because they have the same direction. Therefore, that we expect the total gravitational force between the ruler and point mass m is the summation of all the little dFg. That gives us this result. Now what do we do? Since our ruler, this extended body, starts from x equals 0 and at x equal to L, so we say 0 to L. Now, we need to finish this integral. This is a mass procedure. So what we do is, well, assume that the ruler has a uniform mass. One-dimensional density, we usually use that little mu, that equals to total mass of the ruler divided by total length of the ruler. Since it's uniform, the size we cut is dx. So therefore, dm should equals to the density times its size called dx. Now, we are going to plug in this dm expression into our formula. This integral is from 0 to L, and capital G, m. Our dm is replaced by mu d of x and L plus b minus x of square. Now what do we do next? Well, let's take a look. Constant, constant, constant. So we don't have to worry about it. Well, as far as for the dx, we can add a little negative sign inside, and we time a little negative sign outside. We still balance the equation. Okay. On the other hand, look at this. L plus b is a constant. So as a matter of fact, we learned from calculus that d of L plus b minus x actually comes out as d of negative x. Why is that? Because when you differentiate a constant, that will be 0, then plus you differentiate the negative x, which is this term. This is what's left. So this indicates that the d negative x can be replaced by d of L plus b minus x. So, as you can see, that we have a negative sign and constant g m mu. We can pull this out of the sign of integral, and this d negative x can be replaced by d of L plus b minus x. And we still have that denominator. Well, this time I think you feel more comfortable because you see a pattern of d of something over that something of square. So if I change this pattern a little bit more, I think you will feel even more comfortable. That is, I'm going to get this L plus b minus x at denominator as the numerator. Have this negative 2 in front of it, and d of L plus b minus x. Okay? So, as you can tell, we're going to be able to finish this. Here we go. Now, the result of total gravitational force between the ruler and the point mass should equals to this negative g m of u. Okay. Now, according to the rule integral, that what we come out is negative 2 plus 1 as a coefficient. And then L plus b minus x of negative 2 plus 1 from x equals to 0 to x equals to L. Okay. So, you can see this is negative 1, negative cancels. Capital G, little m. This mu is linear density, replaced by the mass of the ruler divided by length of the ruler. And this actually is 1 over that L plus b minus x. So therefore, if we plug in, what we have is from x equal to L. So this is L plus B. If we plug in x equal to L, that's minus L. Minus of L plus B when x equal to 0. Minus 0 is the result. So L and negative cancels, and the result that we have is G M M. Here is L, and this is 1 over B, and that is 1 over L plus B. Let's take a look at this. First of all, I think the units are right, because gravitational force suppose equal to capital G times the production of two masses divided by the distance squared. So since this is a distance, and this combination also means another distance, so the units is right. However, imagine from the very beginning, if we assume the mass of the ruler is right here as capital M, and this is half L, a point mass of mass little m is little b away from the far end of the ruler. If we directly apply Newton's law of universal gravitation, assuming between this point mass and that point mass, what we have is F of G equals to capital G of capital M, little m, over what is the distance? Little b plus half L. So it is little b plus half L, that distance square. Now obviously, this is completely different compared to that one. So therefore, from the very beginning that I explained, only when your distribution is a spherical symmetric object that you can assume its gravitational mass is at its center. Otherwise, you cannot. So the ruler is not a spherical symmetric object. So we cannot assume the gravitational mass concentrated at its center. We must cut a small slice and name it dm, and we must calculate the gravitational attraction between this point mass dm and that particle m to find the dfg. Then we add all the dfg, and we get our correct result, which is this one. Okay, gravitational force caused object to fall, that we learned from our previous chapters, which is especially from Physics 1A. Now, let's talk about the dynamic of this case. First of all, this is Earth. Since Earth is a spherical symmetric, pretty close to spherical symmetric mass distribution, so we can assume mass of the Earth is concentrated at its center, and this is radius of Earth, RE. If we have a point mass, a little m, h meters above the surface of the Earth, this h actually is altitude. So the separation now between the little m and me, which is mass of the Earth, is re plus h. So assume Earth exert a gravitational attraction on little m. Well, certainly, as a reaction, the little m also exert a force on the center of the Earth, on the mass of the Earth. It's same magnitude, opposite direction. Well, since they have the same magnitude, a force on the little mass will cause very large acceleration. The same amount of force on the large mass of the Earth will cause very small acceleration. Therefore, what we see is that the object falls towards the Earth. We do not see the Earth jumps up because the little m attracts the Earth. Okay, this Fg can be expressed as, since this is a point, assuming this is concentrated center, so it's point mass, capital G, little m, mass of the Earth, divided by their separation square. Separation is Re plus h. Don't forget about this square. Okay. Now we learned that if there's a force on the object, if we ignore the air friction, and when this object falls, that's called so-called free falling, then it will cause an acceleration. So this is a force on the little m, so little m is going to have an acceleration. This acceleration is so special because it's caused by gravitational force. We give a special symbol of little g. This little g stands for gravitational acceleration constant. So if we want to get this value of little g, as you can see, that when mass m cancels, this little g equals to capital G. When the mass cancels, you have this mass of the Earth left and radius of the Earth plus altitude of square. Now, radius of the Earth is very close to 4,000 miles, or we say 6,400 of kilometers. Well, actually, the Earth is a little bit elongated. It has relatively larger radius at the equator compared to the radius to the north or south pole, because 5 billion years ago, when we have a supernova that established our solar system, Earth is relatively hot and soft, but still spinning. Spinning will cause a jello elongated around its orbital region. Therefore, the radius around the equator is a little bit larger compared to the radius to the north or south pole. Okay, now since radius of the Earth is around 6,400 kilometers, if we consider an object near the surface of the Earth, say for example, if you go to the top of Mount Everest, H probably is around 8.4 kilometers. 8.4 kilometers compared to 6,400 kilometers, this is a very small add-on. So when that happens, as long as anything is under the top of Mount Everest, we can ignore this little h and we give this g me over re squared. If we plug in the right number for capital G, which is 6.67 times 10 to negative 11 of SI unit, mass of the Earth is around 5.9 times 10 to the 24 kilogram. And we plug in this in SI unit, which is meter, should be around 6.4 times 10 to the 6 of meter. And what comes out very close to 9.8 of meter per second squared. This is a very useful constant that you will use many times in this chapter. But this is a so-called gravitational acceleration constant near the surface of the Earth. If we consider the gravitational acceleration constant near other terrestrial planets, for example, if we calculate G on the Mars, then we have to plug in the mass of the Mars here and the radius of Mars here. And after the calculation, we will get the G near the surface of Mars. And I mentioned that only when h, the altitude, is relatively small compared to the radius of the Earth, and you can ignore this little h. Otherwise, that you have to take that h into consideration. For example, if we talk about variation of g with altitude h, on your textbook, page 395, there is a table. It gives us a list of very interesting results that tells us that when the h goes very large, and the little g will decrease dramatically. For example, when altitude h is 1,000 kilometers, the g will come out as 7.33 meter per second squared. And if we reach 2,000 kilometers, which means we doubled altitude, that g will drop to 5.68 of meter per second squared. So let's see. When h is 1,000 kilometers, the g is already smaller than 9.8 meter per second square. It is 7.33 of meter per second square. And when h is 2,000 of kilometer, well, pay attention, we're not going to get half of that, okay? And the result is 5.68 of meter per second square. So little g varies according to its altitude. And one more thing I want to mention is that the G around the equatorial region is slightly smaller than the G at the North Pole, South Pole, because look at this equation. If we're near the surface of the Earth, we can ignore H. But when you plug in radius of the Earth around the equator, this RE is relatively bigger compared to the radius of the Earth of North Pole or South Pole. So the G at North Pole, South Pole will relatively bigger compared to the G at equator. So for example, the country as Sweden, which is pretty close to the North Pole, and the G value is around 9.83 of meter per second square. But the country near the equator probably will have a G of 9.73 meter per second square. That is the variation due to the latitude we call. Okay. Next, we're going to learn Keplers Laws. Let's take a look at what is Keplers Laws. Kepler has 3 laws. Kepler's first law says that all planets move in elliptical orbits with the sun at one focus. So see, look at the orbit. It is so-called elliptical and with sun at one focus. Kepler's second law says the radius vector R drawn from the sun to a planet, which is right here, that's a planet of M of P, sweeps out equal areas. When the planet moves, that vector R will sweep out the area, let's call dA, will sweep out equal area in equal time intervals. What does that mean? For example, if we consider a dt time interval, and when the planet has a large R, and it will sweep out a skinny area of dA. Now imagine if our planet is right here and with a relatively small R, for the same time interval of dt, it has to sweep out the same amount of area, so therefore we have to get a slice of area of equal to that slim one. So for the same dt time, the planet actually moves smaller angle compared to a planet when it is closer to the sun. It has to move through a larger angle. And we know that can be expressed by angular velocity omega. That is the angle turned over the time. So for the same time dt, if the angle d theta is larger, then you have a larger angular velocity. So we say that when the planet is relatively away from the sun, it has a smaller angular velocity. When the planet is close to the sun, it has a very large angular velocity. So that is the second law of Kepler. It says the radius vector drawn from the sun to a planet sweeps out equal areas in equal time intervals. Kepler's third law says the square of the orbital period of any planet is proportional to the cube of the semi-major axis of elliptic orbit. Now, semi-major axis, let's look at this elliptical orbit. Well, any elliptical orbit should have 2 focus, F1, F2, and this direction, little a defined as semi-major, little b defined as semi-minor. And the relationship between A, B, and C, what is C? C is the distance from one focus to the center of this orbit. That is C. The relationship between A, B, C is A squared plus B squared equals to C squared. And this C has special meaning. We define C over A as eccentricity. Now imagine if F1, F2 both focus move to the center. When F2 approach to here, isn't that C equal to 0? So when 2 focus goes to the center of the orbit become 1, and we have a circular orbit. So a circular orbit C equals to 0. Therefore, the eccentricity for circular orbit equals to 0. So if you have a larger eccentricity, which means that the orbit is very much elongated, like the orbit of Pluto, it's very much elongated. That makes that sometimes Pluto is even closer compared to Neptune, because when the orbit is very much elongated, it has a chance getting very close to the sun. Okay. Now I'm going to prove Kepler's second law. Kepler's second law, we just learned that radius vector drawn from the sun to a planet sweep out a area. We name it dA in the time of dt. So if the planet moves as velocity v, and v times dt give us the distance it travels, and the area of this triangle dA equals to 1/2 base times the height. Because it's very small, you can view this as triangle. The height is the vector r. And on the other hand, that the force between the sun and planet is that of gravitational force Fg. It is gravitational attraction force. According to the definition of a torque defined as the force cross the lever arm. So in this case, our lever arm is that vector r. Obviously, it has a 180 degrees angle with respect to the attractive force Fg. So when the lever arm has a 180 degrees angle with the force, then r cross F is Rf sine 180. That equals to 0. Therefore, in this case, that torque caused by gravitational force equals to 0. We learned from previous chapter that when a torque equals 0, then since this is the only torque on the planet, and then sigma torque also equals to 0. On the other hand, sigma torque equals to d angular momentum over dt, the rate of change of angular momentum. When the rate of change of angular momentum equal to 0, the angular momentum is constant. L is a constant. Well, L defined as r cross p. R is this position vector r. And p is the linear momentum of our planet. That is the mass of planet times its linear instantaneous velocity v. So our angular momentum equals to r cross this linear momentum mpv. Now, since we already know that dA equals 1/2 of base times height. So if we continue on that, we have that dA equals to, now we can replace that our R and V. You see this R, you see this V? Because in our case, R and MP, as a matter of fact, this is the tangential velocity. So when we have a vector cross another vector, that is this vector magnitude times that times sine of the angle between them. Right now, radius and tangential is 90 degrees. Sine 90 is equal to 1. So the angular momentum, as a matter of fact, is mass of the planet and R, the magnitude, and R times V. So we have this dA can be expressed as, since dA is 1/2 of that R V dt, if we move this R in, and we can replace by the magnitude of the angular momentum, and we get that L over 2 MP and dt. So what's replaced is actually this and that, because dt is still here and the 1/2 is still here. So we replace this R and V, that equals the magnitude of angular moment divided by mass of planet. That is this pair we replaced. Okay, so let's take a look. Now, if we differential this area with dt, this dt will be gone. So we have that L over twice of mass of planet. Now, since we already reached the conclusion that angular momentum is a constant because the total torque on the planet is equal to 0. So if this is a constant, mass of planet is constant, then the rate of dA dt is a constant. So this is the so-called Kepler's second law that says that the radius vector drawn from the sun to a planet sweep out an area in the equal areas in equal time interval, which means dA dt is constant. Equal area, equal time intervals. That is Kepler's second law. Now let's take a look at Kepler's third law. Kepler's third law says the square of the orbital period of any planet is proportional to the cube of semi-major axis of elliptical orbit. Now, imagine that this is a planet, mass MP, this is the mass of the sun, and this is the radius. Well, if the orbit is elliptical, and we can replace this r by the semi-major little a. So I'm going to prove this by using a circular orbit. So first of all, we learned that sun will attract the planet with a gravitational force F of g. Fg equals to capital G, mass of the sun, mass of the planet, divided by the separation square. Since this is, let's assume this is a circular orbit, then that equals that planet does circular motion, so that equals mass of the planet times its centripetal acceleration, and centripetal acceleration is v squared over r. This v is the tangential speed of circular motion. So we can easily get this v equals to 2 pi r divided by the period. So if we look at this equation, that mass of planet simply cancels. We have capital G, mass of the sun, over r squared equals to, on the other side is v squared over r. V can be replaced by 2 pi r divided by period. V is squared right here because centripetal acceleration is v squared over r, and divided by this little r. As you can see, one of r cancels, but here is r squared. If we combine everything, the result comes out as t squared over r cubed equals to 4 pi squared divided by capital G, mass of the sun. So this is the so-called the square of orbital period of any planet is proportional to the cube. If you move this one to here, then it's proportional because this is a constant. So we can express in this way. T squared equals to a constant k times the orbital radius to the cube. And if it's elliptical orbit, we can replace this little r by a of the cube. This k is a constant. Now if we just calculate the k for the solar system, which is the planet rotate around the sun, then we're plugging the mass of the sun here. And we do have this table list all 9 planets rotate around the sun, and give us this constant k very close to that 2.9 of 10 to negative 19. That is on page 399 of your textbook, for table 13.2. Now let's use this Kepler's third law, which this is third law. to calculate something, there's a so-called geosynchronous orbit. What is it? Well, imagine this is a top view from the North Pole, and Earth rotates from west to east, and rotate like that. And this is the North Pole. Okay, well, there's a city on the surface of the Earth, so it is how far away from the center of the Earth? That's 1 RE. Now imagine we have a satellite, a certain height above the surface of the Earth. What we want is when the city finish one rotation, that takes 24 hours, 1 day, that satellite also finish that one complete rotation, which means the satellite is always above that particular city. So we can send signal to the satellite. This satellite can relay to another satellite, so we can send our signal to another city, which is maybe on the other side of the Earth. This is so-called the geosynchronous orbit. How far exactly this orbit above the surface of the Earth? Well, the height is relatively close to 6 of RE. I'm going to prove that. So let's start from here. This is a circular orbit because the satellite rotates about the center of the Earth. Now, if we want the satellite to finish one rotation in 1 day, just as the Earth finished one rotation in 1 day, so period is 1 day, that is 86,400 seconds. Now, we're going to find out what is the separation R between the satellite and center of the Earth, since this is the orbital radius. And again, this is satellite rotate around the Earth, so this is mass of the Earth. Right now, if we are interested in this R, so we need to place everything else on the other side. So 4 pi square of G, mass of the Earth, and okay, if we do this, it's the other way around. Sorry, okay, let's say that should be the other way around. Okay, let's say that we are interested in R, so this goes here, and then we have this G M E T square on the numerator and the 4 pi square on the denominator. If we plug in the right number for capital G, mass of the Earth, be careful T, you cannot plug in 1 day because everything must be in SI unit. So SI unit for G, 6.67 times 10 to negative 11. Mass of the Earth, 5.98 times 10 to the 24 kilogram. T, right here, you have to plug in that 8.64 times 10 to the 4 of second because that's SI unit. Don't forget about square. And then 4 pi square. And you can get this R cubed. Later you do the cube root, and you will find that actually the R comes out as 4.2, very close to 4.2, times 10 to the 7 of meter. Well, compared to the radius of the Earth, that is 6.4 times 10 to the 6 of meter. So isn't that true? The ratio is close to 7. And if capital R is 7, which is from the center of the Earth to the orbit, if this is 7 of RE, isn't that true? After we subtract 1 RE, the height will become 6 RE. This is how high the satellite has to be in order to be in the geosynchronous orbit. Next, let's learn something which is slightly different. That first of all is the gravitational field. Imagine we have a large mass of m and we have a small mass of little m, and obviously we know that the large mass will attract the small one. Well, certainly the small one also attract the large one, but right now we're interested in the small one. So the gravitational force on small one is Fg, that is that follows Newton's law of universal gravitation. Well, if that we define gravitational field, that is a vector, has a symbol a little g, that's a vector, equals the gravitational force divided by the mass of this particle then we will come out as, if this capital M is a spherical symmetric mass distribution, then we can assume this is concentrated center. So if we know the separation of R from the center of this guy to the point mass M, we have this gravitational force equal to capital G mass M little m over R squared divided by little m. So we'll get that. That is obviously the magnitude, and the direction should always point to the large mass M. This is called centripetal, which means center seeking. So that's why when the little m is here, it's center seeking. And you can imagine if you have a little m right here, and the direction of gravitational field will be toward the center of large M. A field, gravitational field, means that the test mass is in the area that will be affected by the gravitational attraction of this capital M. That is just a concept. However, the very useful thing mathematically that we're going to learn is the next one, is gravitational potential energy. Now, we learned from previous chapter that a potential energy should connect to a conservative force. The definition of conservative force is that force, if there's a particle and there's a force on this particle, if that particle moves a distance dr, and this symbol means you finish a closed path, you start from point A, you go somewhere, you're back to A, that's closed path. If this integral comes out equal to 0, then that force F is a conservative force. Very weird definition. Well, that is from your for survey book, that is chapter 8, definition of conservative force. A conservative force will associate with a potential energy. So you see, if we have this called gravitational potential energy, therefore that indicates that gravitational force is a conservative force. I am going to prove that. First of all, let's look at the situation. If this is Earth, and mass of the Earth, assume it's at the center, and we have a particle right here of mass little m. Initially, it is located at point A, and under the influence of gravity of Fg, initial position vector is r of I. And then if this particle somehow moved to position B, and this is the passage, and well, at position B, gravitational force still be center seeking, so that is the direction toward the center of the Earth. And final position vector is r of F. Now, we're going to look at this case and to see how can we prove that the gravitational force here, Fg, is a conservative force. There's something very interesting that I want to point out. When a particle of mass m starts from A, if it has to move tangentially with a little distance called d of s, that's two-dimensional displacement. Any two-dimensional displacement can be split into that of this one is, let's say, it's center seeking, it's around the radius direction, and the other one is the tangential. Now ds is tangential to the path, but this part is tangential to the radius because that is the radius of r of initial. So, which tells us that any of ds, which is like that, can be split into that ds of this and ds of that. That is called ds of radius. That's called ds of radius and ds of tangential. Okay, let's continue. Work done defined as F dot ds, force dot displacement from point A to B. So let's say this is Earth, and that is a particle of mass m starting from point A goes to point B. And I explained that any ds tangential to the path can be split to the ds of radius direction of ds of tangential to radius direction. So we have the ds equals to ds of r plus ds of tangential. Okay, so let's take a look at work done equals to, if it's a to b of f dot, we replace ds by ds of r plus ds of tangential. Be careful, both are vectors. Now, in this case, the force is always center seeking because that is gravitational attraction force. So that is opposite direction of the radius. So when we have gravitational force F dot that the ds tangential, that will come out 0 because the angle between gravitational force and tangential direction is 90 degrees. A dot B, if AB has a 90 degrees angle, that equals 0. So the result will have this gravitational force F of G dot ds of R left. Now, since gravitational force is center seeking and dsr is radius direction, so when they dot, the angle is 180 degrees. So, I'm sorry, when they dot, it is a cosine. So, AB cosine 180 is a negative sign. Negative, and we're going to plug in the magnitude of gravitational force, which is G between mass of the Earth and mass of that point, divided by the separation square, and since this is the radius direction, that is simply dr. Okay, as we can see that these are constants and we can pull this out of it. So negative a to the b, well, we can move the constant out of this. Well, this constant is the combination of constants right there. And then divide by r squared is r to negative 2 of dr. So the result is negative of constant, well, comes out. And the integral of this will be negative 2 plus 1 as denominator, and r to the negative 2 plus 1 from initial r of initial to r of final. So if we look into this result, this negative, that negative cancel. We have g m e of m, that when we have this 1 over rf minus 1 over r initial. Now let's take a look. If we start from A, it goes to somewhere, but eventually come back to A, isn't that true? Our final initial positions are the same because it finished a complete passage. When that's same, then this will be 0. So work done by gravitational force for a complete passage equals to 0. Conclusion: gravitational force is a conservative force. This is what we just got. Work done by gravitational force equals to that. Now, if work done by a conservative force, that according to what we learned should equal to the negative change of its potential energy, and change means potential energy final minus potential energy initial. So what does that mean? That means that if we look at in the final minus initial, there's a negative sign. If we move this negative sign to the left side, what we have is, as a matter of fact, is negative of g m e m over r final, because this negative sign gets here, minus, negative sign getting here is plus, but minus a negative is plus. That is g m e m over r initial. What does that tell us? That tells us that final potential, which has this expression, initial potential, which has this expression. So potential energy, gravitational, has expression negative g m e m over r. What is r? Well, that is the position vector, that the little m away from center of the earth. This should be able to apply to any two particles has a separation of r. So it's g m1 m2 over r. or this can be applied to spherical symmetric objects. Then you can assume the mass concentrated at the center of spherical distribution. So gravitational potential is a negative thing. And also, please notice when r equals to infinite, what does that mean? That means when a particle is infinite away from another one. If m1, m2 has a separation r infinite, then u equals to 0, which means when an object is infinite far away from another one, the gravitational potential energy is 0. Let's think about this. Somehow, one particle step into other particle's gravitational field. We just learned that. So it will be affected by the gravitational attraction force. And then if there's force, there will be acceleration. So the particle will speed up, or we say simply move towards the attraction of the center. Now, when the object speeds up, it picks up kinetic energy. However, well, if only between two particles, the only force is gravitational force, then the system's mechanical energy is conserved. If a particle picks up kinetic energy, then, well, it has to lose from something. Then what happens is the total mechanical energy is kinetic plus potential. If it's a constant, then initially that when a particle is infinite far away, that u equals 0. If this is 0, and then if kinetic energy initially is also 0 because the particle does not move. Now, eventually, if this becomes positive, then this must be 0. But this must be negative, I'm sorry, because that constant is simply 0. When two particles are infinite away from each other, the potential energy is 0, the kinetic energy is 0 because they do not move. 0 plus 0 equal to 0. When Ke becomes positive, U has to be negative. That is why potential energy has a negative sign. So let's talk about energy. Let's have energy consideration about planetary and satellite motion. Imagine that this is Earth, and that is the radius of the Earth, and we have satellite, which is h meters above the surface of the Earth. That's a satellite. And so the definition of its radius is that radius of the Earth plus the altitude h. And if it's in the circuitry orbit, the tangential velocity is v. The total energy of the satellite, E, equals to kinetic energy plus its potential energy. Kinetic is 1/2 mv squared. Potential energy is negative of, that is the Earth. So it's mass of the Earth as it concentrates the center, and has a g, and a mass of the satellite. And then we have this r square. No square. That's potential energy has no square. Okay. On the other hand, the reason the satellite rotates around the Earth is because of gravitational attraction F of g. Gravitational attraction between the Earth and the satellite follows this Newton's law of universal gravitation. That equals to the mass of the satellite, because that's a force times a centripetal acceleration. That centripetal acceleration is v squared over r. Now the left side, as right here, is capital G, mass of the Earth, mass of the satellite, over r squared. Now if we look at 1/2 of msv squared, which is what we need, because the kinetic energy here is the kinetic energy of satellite, so it's 1/2 msv squared. Obviously, we can cancel 1 over r. So kinetic energy of the satellite can be replaced by capital G, mass of the Earth, mass of the satellite, over r. So we have that capital G, mass of the Earth, mass of the satellite, over of r. And on the other hand, because initially we have this equals to that. This 1/2 we time to the right. We should also time a 1/2 to the left. So that should be like this. And then the second term is a minus of g, mass of the Earth, mass of the satellite, over r. So if you look at it, you can view this as 2 over 2. So the result is negative of g, mass of the Earth, mass of the satellite, over 2r. That is the total energy of the satellite in a circular orbit.